So we are trying to do what is known as the steady state analysis of a general converter. So we saw that if we can get some quantities, uh, for example, A1, U1, A2, U2, then C, D, we can actually we can solve the equations for a given value of alpha. Of course, the other quantities like omega O is known for a system, then T1 is also known. So the uppercase T with the subscript 1 is known. So in general, we have to find A1, U1, A2, U2, C, D, F, G. So we will try to find the quantities A1, U1, A2, U2, C, D, F, G. Of course, to find A1, U1, A2, U2, and of course the other quantity C, D, F, G, we need to also say what is the vector x1, what is the vector x2. So what are the elements of x1 and x2? So we need to also know x1 and x2. Okay. Now let us take some special cases. I mean, first we'll consider the cases that we have already studied, then take up new cases. Okay. So the cases that we have already studied are very straightforward. So if I take the case that is already considered, that is 6 pulse LCC with constant current on the DC side and a 3-phase balanced voltage with inductance in each phase on the AC side. Thank you. One, three, 5, 4, 6, 2. So this is our circuit. Now we will take one case which is already known to us, that is say 3 and 4 level conduction mode. Okay. So we will also consider 2 and 3 level conduction mode. So 3 and 4 valve conduction mode. Now, what can be the state vector x1 and what can be the state vector x2? See, there is one fact about x1 and x2, that is x1 is just larger than x2 by 1. Okay. So and the last element of x1 without loss of generality is the current in the outgoing valve. The current in the valve that stops conducting. So which valve stops conducting? When I take 3 and 4 valve conduction mode, in the first subinterval, one valve stops conducting. 6. So the second element, which is, okay, first of all, what is the size of x1? Size of x1 is 4. So it has 4 elements. How? How it has 4 elements? How does it have 4 elements? See, 4 valves are conducting, but are there 4 state variables? You are familiar with circuit analysis, right? I mean, you do loop analysis, node analysis. Here, we already considered analysis of such circuits. I mean, we did actually loop or mesh analysis. So, how many loops are there? Huh? 3 loops, but one of the currents is known. See, ID is something which is given to us. Okay, so the current source is something which is known. So, one of the currents is ID, which is a loop current which is known. So, there are only 2 loops. Okay, so I can say that X1 is having 2 elements. So, I also know that the second element or the last element of X1 is I6. What about the first element of X1? So, the first element of X1 is also the element of X2. So, now X2 is only having one element. It's just has one element. So, how do you take the first element of X1? See, one point to note is that the state vector is not unique, but based on the fact that the last element becomes 0 as far as X1 is concerned, we take that as I6. So, one of the elements of X1 is fixed. So, the other elements of X1 are nothing but the elements of X2. It seems we have a freedom. We have a freedom. See, in general, we have a freedom. Okay, but for this type of analysis, whether do we have a freedom is the question. Say, there are so many other quantities to be determined. A1, U1, A2, U2, C, D, F, G. Now, there is one equation which actually relates X1 and X2. What is that? In fact, there are 2 equations. One is related through D. The other one is related through F1G. So, that gives a hint about what can be the other elements of X1 and X2. In fact, D is also a known matrix. D is a known matrix. So, if you take the other equation which relates X1 and X2 through F1G, that gives some hint. See, so I said that I will just assume one equation like this: X1 at alpha by omega O is equal to F into X2 at alpha by omega O plus T1 plus G, where F1 G are constant matrices. F1 G are constant matrices. Now the question is how to choose X1 and X2 such that I satisfy this equation. So if I take element wise, there are 2 elements in X1. The last element is known, I6 at alpha by omega O. This is equal to a matrix F. Now what is the size of this matrix F? See, once I know this matrix X1 is of size 2 cross 1, matrix X2 is of size 1 cross 1. So what is the size of F? Huh? 2 cross 1. So it is 2 cross 1. So this is a 2 cross 1 matrix into X2. Okay. So I have to find X2. So I will fill that X2 here. Plus I will multiply this matrix F by X2 plus G. What is the size of G? 2 cross 1. Okay. Now I have not written X2 because I have still not written X1 completely. The first element of X1 is nothing but X2. Now the question is what can be chosen for X2, which is nothing but the other element of X1 or the first element of X1. Say I have to okay, if I assume that the quantity that I choose is one of the currents. Okay, so the element of x1, the first element of x1. So that current is evaluated at alpha by omega O plus T1. So what is that current? I1. Okay, suppose it is I1. Suppose it is I1. Then the left hand side is I1 at alpha by omega O. Suppose, okay, suppose this works. Let us see whether we can get F and G. So what is the first element of F? What is I1 at alpha by omega O? Three and 4 valve conduction mode. What is I1? Huh? ID. It is ID. So it's ID. So then can you tell me what should be the first element of F? What should be the first element of G? Okay, see what I am trying to say is I1 at alpha by omega O is known quantity, that is equal to ID. Then can I relate I6 at alpha by omega O and I1 at alpha by omega O plus T1? Are the two related? Can I relate I1 at alpha by omega O and I1 at alpha by omega O plus T1? Are the two related? Say this T1 is one interval. Uppercase T1 is one interval, that is 60 degrees. Now we are doing everything in time because our equations are differential equations where the independent variable is time. So that's why we have changed everything to time for the time being. So how are these two related? I6 at alpha by omega O and I1 at alpha by omega O plus T1. Huh? 0. Both are 0. See, at alpha by omega O, what is I6? I mean, is it 0? Now my only question is whether these two are related. See, one point to notice, all the valve currents are identical except for a phase shift of 60 degrees. In time it is uppercase T1. 60 degrees is one interval, uppercase T with a subscript 1 is one interval. So whatever happens to I6 happens to I1 after 60 degrees or after T1. So they are equal. They are equal. Now from these two equations, can I fill the elements of F and G? So the only constraint is that F and G are constants. Okay. So what are the elements of F? What is the second element of F? 1. What is the second element of G? 0. That is easy. First element of F? 0. Oh, sorry. 0. The second element of F? First element of G? ID. ID is a constant. So this works. So this choice of x1 or x2 works. So that means I can take this x1 as I1 I6 and x2 as I1. This works. We don't know whether something else also works. I mean, we will be happy as long as the one which you are trying works. Okay. So one can try to find out if any other choice of x1 and x2 will serve the same purpose. Say my intention is to relate x1 at alpha by omega O and x2 at alpha by omega O plus T1 through F and G, where F and G are constants. So this is something which is actually satisfied always. So after looking at many cases, people have arrived at this equation. So I just gave it as just a statement without proving. Now we saw that it actually gets satisfied for 3 and 4 valve conduction mode. So it's not only for 3 and 4, we can see that it also is satisfied for 2 and 3 valve conduction mode and also for other circuits. This is the simplest circuit. Okay. Now let us get the other quantities A1, U1, A2, U2. And of course, see, please note this C and D. C and D matrices are actually known in advance if I know what is the size of x1, what is the size of x2. So C and D is something which is very easy to find out. Okay, so C and D is I will not try to find C and D, but A1, U1, A2, U2, and F and G are to be known. So what is A1? What is A1? So first of all, what is the size of A1? So it is of size 2 by 2. 2 by 2. Okay, if it's difficult to say what is A1, what is U1? That may be easy. Okay, what one needs to do is get the equation. Okay, let us do that. See, our circuit is like this. If I just retain the elements through which there is a non-zero current, so this is the circuit which is applicable for the first subinterval. So I have EA, EB, EC, L, L, L. So I have val 1, then below that I have val 3, then this is val 6, this is val 2. So I have taken one of the currents, valve currents, that is I6, as an element of X1. So I6 is one of the elements, and of course the other element that I have taken is I1. The other element of X1 is I1. So it's just a matter of applying Kirchhoff's voltage law and get the equation. That's all. So I have to get two first order differential equations. From that I will get A1 U1, A2 U2. Of course A2 and U2 are from the second subinterval. So this circuit is for first subinterval. So this is for the first subinterval. So what are the equations? If I apply Kirchhoff's law, L d I1 by dt. So what is this current? The current which is flowing through or leaving EB from the positive from the positive terminal. Because if I want the voltage drop across the inductance in series with EB, means I should know the current through EB. So can I write this current in terms of I1 and I6? ID minus
bracket I1 plus I6.
ID minus I1. So ID minus I1 gives I3 minus I6. So if I apply Kirchhoff's voltage law, minus L d by dt of ID minus I1 minus I6. So this is equal to what? Equal to what? A minus EB. So I have to just simplify this. So get the equation. That's all. I need not solve. See, please note I have to just get the equation in the standard form. See, the standard form is a first order differential equation where I have on the left hand side the first derivative of the state variable with respect to time. The right hand side is actually a linear function of states and input in general. So what I need on the left hand side is the derivatives, but the thing is I will have not in the required form because there are I mean there are both state variables I1 and I6 in the same equation. So okay, what I will do is I will first write the other equation also and then try to simplify. So if I take the second loop apply Kirchhoff's voltage law, I get L d by dt of id minus I1 minus I6 minus L. What is the current? Okay, if I take in this direction, what is the current here? id minus I6 plus L d by dt of id minus I6. This is equal to EB minus EC. So this can be written as a matrix times, so there is both di1 by dt, di6 by dt. So I will write this as di1 by dt, di6 by dt. So I will push this L onto the right hand side, and the right hand side becomes EA minus EB by L and EB minus EC by L. So the coefficients that remain are, so coefficient of di1 by dt on the in the first equation on the left hand side is 2, and the coefficient of di6 by dt is 1. Then in the second equation, the coefficient of di1 by dt is minus 1, and the coefficient of di6 by dt is minus 2. Okay. So this is our equation. So to get it in the standard form, pre-multiply both sides of the equation by the inverse of this square matrix containing elements 2, 1, minus 1, 2. So the standard form is this: di1 by dt di6 by dt. This is equal to what? What is this matrix? EA minus EB minus EC. What is the inverse of this?
Minus 1 by 3 into minus 2.
Minus 1?
Directly 2 by 3.
2 by 3. So it is 2EA minus 2EB plus EB minus EC. What is this? EA? EA by L. Similarly, what is the second term? What is minus EA minus plus EB minus 2 EB plus 2 EC? EC? EC by L. So of course we know what is EA and what is EC. Of course, if I just substitute that, I get this as equal to root 2 by 3 V sine omega OT plus 150 degrees divided by L. V by L sine omega ot minus 90 degrees. So this is the equation. So this is the right hand side of the equation. The left hand side is of course di1 by dt, di6 by dt. What is a1? Okay, let us go back to the view. What is a1? Huh? It's a zero matrix. It is 0 0 0 0. And u1 is what is there on the right hand side of the equation that we derived. So it is root 2 by 3 v by l sine omega ot plus 150 degrees, root 2 by 3 v by l sine omega ot minus 90 degrees. So this is u1. Now if we want a2 and u2, we have to just consider the second subinterval. So far what we have done is we have found a1 u1, but before that we also found fg. Please note this is f. This matrix 0 1 is f and this matrix id0 is g. Okay. So the only thing to be determined is a2 u2. I mean C and D are known matrices. Once we know the size of x1 or x2, we know the matrices C and D. So what is what is a2? What is u2? For that we have to consider the second subinterval. So second subinterval. So let us consider the second subinterval. So if I just show only those elements through which there is a non-zero current, so in the second subinterval, valve 6 is not conducting. So I have EA, EB, EC, L, L, L. So we have valves 1, 3 and 2 conducting. So in the second subinterval, we have only how many state variables we have? Only one state variable. What is that state variable? I1. So I'll just show this state variable I1 here. So there are two loops. One of the loop currents ID is known. So I have to just write the equation for I1. So if I apply Kirchhoff's voltage law, I get the equation L di1 by dt, and the current through this inductance connected in series with EB is ID minus I1. So what I have is L di1 by dt minus L d by dt of ID minus I1 is equal to EA minus EB. So the standard form is the derivative, the first order derivative on the left hand side, the rest of the terms on the right hand side. So I should have only di1 by dt on the left hand side. So what is there on the right hand side? EA minus EB divided by 2L. So EA minus EB is actually a line voltage. So I can write this as, so what is EA minus EB? Huh? Yeah, minus root 2V. So there is a 2 in the denominator, so I can write this as V by root 2L with a negative sign, sine omega ot. Now, can I say what is A2 and what is U2? Of course, the size of A2 is 1 by 1, U2 is 1 by 1. Okay. So, what is U2? Minus V by root 2L sine omega ot, and A2 is 0. Now, you notice that A1 is 0, A2 is 0. Now, because A1 and A2 are 0, the circuit was easy to analyze. So, we will consider some cases where A1 and A2 are not 0. So, if A1 and A2 are not 0 matrices, though we know the solution, it is slightly complicated. Okay. Now, before going to other cases where A1 and A2 are non-zero, let us consider the same circuit, but what we have now is 2 and 3 valve conduction. See, already is what we see in just now is 3 and 4 valve conduction. So, if I take the same circuit and consider 2 and 3 valve conduction mode, which is actually the normal mode of operation. Now, can you tell me what is x1? What is x2? First of all, what is the size of x1? What is the size of x1? Size, forget x1. Huh? There are, if you look at the circuit, there are two loops. One loop current is known, so there is only one element. So it is just one element. Okay. Then what about x2? Does not exist. Does not exist. Now we will introduce what is known as empty matrix. So I'll come back to 2 and 3 valve conduction mode, but I'll just deviate by trying to define. This is not something which is defined for this purpose. Empty matrices are used in other areas also. Okay. Now we know that a matrix is of size, say, m cross n, means it has m rows, n columns. Now, most of the times m and n are positive integers. Now, if one of them is 0, now why do we get one of them 0? We will see that it's easy to generalize a few things by taking either number of rows or number of columns as 0. If one of them is 0, or if both are 0, one of them means one of m, either m or n or both are 0, then we get what is known as empty matrix. So, if m is 0 or n is 0 or m and n both are 0, then suppose, okay, the matrix is said to be empty. Now, at this stage, it's not clear what is the difference between a matrix which has 0 rows and say 1 column and 0 row and 0 column. Now, it becomes clear only when we consider some special cases. Okay, so right now we will just accept that either a row can be 0, number of rows can be 0, or number of columns can be 0. Okay, and both can also be 0. Everything is possible. Now, we know how to do matrix multiplication. Suppose I have a matrix A of size m cross m. I have a matrix B of size P cross Q. Now, suppose P is equal to n. So, let me take that. Suppose this P is equal to n, or B is as good as saying B is n cross Q. Then I can define the product AB. So AB is of size M cross Q. So we will make some assumption. Let M be greater than 0. Let Q be greater than 0. Let N be 0. Then A is an empty matrix. A is empty matrix because number of the columns is 0. B is also empty matrix because number of rows is 0. But what happens to AB? AB is not a. See, if you look at M is not 0, Q is not 0. Okay, so matrix multiplication is still defined if one of the number of rows or number of columns is 0, as long as the number of columns in the first matrix is equal to the number of rows in the second matrix. That's the only condition required for matrix multiplication. So here it is satisfied. But it so happens that n is 0. So if n is 0, then we have A and B empty matrices, but AB, the product, is not empty. Okay, so in that case we define then AB is a M cross Q 0 matrix. So that's the definition. So if I have two empty matrices but whose product is not empty, then by definition its product is 0. So this is just a definition. Take it as a definition. Okay, it's just definition. I mean, one need not be even bothered why we are trying to do like that. It's just a definition. Okay, so doing this definition will help us in all the future analysis. Now we will define a few more things. We say in the solution you see what is known as exponential of a matrix. So, but when it comes to exponential, what we have seen is we have not considered, I mean, exponential for any arbitrary matrix. I mean, exponential is always for a, that's all we know at this stage. I mean, we have just defined exponential of a square matrix. So when it comes to exponential of a empty matrix, so the empty matrix should also be square. See, square means number of columns is equal to number of rows. So the exponential of a 0 by 0 matrix, so I have an exponential of a square empty matrix is 0 by 0 matrix. That's again a definition. So if I have a square empty matrix, the exponential of that is also a square empty matrix. Then in the solution, see, in the generalized solution, we also have what is known as an integral. So there is an integral of empty matrix which can come as a possibility. Say exponential comes in the integral, exponential minus a tau, a1 tau or a2 tau into u1 tau or u2 tau d tau. Okay, so if a1 or a2 is an empty matrix, then exponential by definition is also empty matrix. Okay, so if you take the product of that empty matrix with u1 or u2, what do you get?
Can we take the product?
Yeah, we can take product provided u1 and u2 should also be empty. Okay, so I mean the matrix dimensions actually match in that way. So we'll see that. So it so happens that if exponential of a matrix is empty, it's getting multiplied by u1 or u2, that is also empty. So what we get is a resultant column vector which is also empty. So what is the integral of that? See, the second term in the solution involves an integral. So by definition, the integral of an empty matrix is also an empty matrix. See, we take integral with respect to tau, right? So integral of an empty matrix is an empty matrix. Okay. Now, with this information, can we go back and see what is x1 and what is x2? What is x2?
0 cross 1.
Yeah. See, by definition, our state vectors are column matrices. So it should have one column. Okay. So it can be empty means the number of rows should be 0. So x2 is an empty matrix. I denote a empty matrix just by square brackets without writing anything within the brackets. Okay. So I mean, if you want, you can note down this is a 0 cross 1 empty matrix. What about x1? No. Yeah, what can be the element of x1? I1. X1 is just I1. Then what about A1? Say, one thing to note is that in the first interval of 2 and 3 valve conduction mode, we have a circuit which is same as the circuit of the second interval of
3 and 4.
3 and 4 valve conduction mode. So the same equation holds here. I mean, the same expression holds for A1 and U1. See, A1 and U1 for this case is same as A2 and U2 for the previous 3 and 4 valve conduction mode that we saw. So what is A1?
0.
0. And U1 we just now found
Minus V by root 2.
minus V by root 2L sine omega OT. Okay. Then what about A2? A2? Empty. So whenever we write empty, I mean, we better to write the dimension, because empty does not just say whether it is 0 rows or 0 columns or both are 0. So in this case,
0 cross 0.
it is 0 by 0. Yeah, 0 cross 0 empty matrix. What about U2? U2 is also
0 cross 1.
yeah 0 cross 1 empty matrix. C and D are obvious. I mean, once I know the size of x1 and or size of x2, C and D are obvious. But what is not obvious is F and G. So how to find F and G? Say, I have the relation x1 at alpha by omega O is equal to F into x2 at alpha by omega O plus T1 plus G. Okay. Now x1 is nothing but I1 is equal to F into x2. What is x2? x2 is empty. x2 is empty. So it is F into x2 at alpha by omega O plus T1 plus G. So if x2 is empty, so x2 itself is empty means x2 evaluated at any instant is also empty. So this is an empty matrix. So this is of size 0 cross 1. So this is a 0 cross 1 empty matrix. So what is the size of F?
1 cross 0.
So it's also an empty matrix. So it's an empty matrix of size 1 cross 0. So now you see that the first term on the right hand side, F is empty, x2 is empty, but product of F and x2 is non-empty.
Cross 1.
Okay, so it is non-empty, it's 1 cross 1, and by definition
It's a 0.
it's a 0. So here it is just 1 cross 1, it's 0. So I1 at alpha by omega is just G. So what is G?
X1 at alpha by omega 0.
No, what is that? ID. ID. Okay. So here also you notice that A1 and A2, of course A2 is empty, A1 is 0. So the analysis was very easy so far because A1 and A2 are actually 0 matrices, if not empty. Now when the A1 and A2 are not 0 matrices, don't get confused between 0 and empty. 0 is different, empty is different. Okay. The two are different. So if I have 0 A1 and A2, the solution is very easy. So I have to just integrate, that's all. I have to integrate something with respect to tau and get here I have to actually use the solution of linear differential equation if A1 and A2 are non-zero. So in the next class, we will consider more complicated circuits for which we will not do any analysis separately. We will just use the general analysis that is applicable for any circuit and try to just get x1, x2, a1, a2, u1, u2, f and g. Okay, so we will try to consider other complicated circuits and try to do a very generalized analysis without going into specialized analysis for any of the circuits in future. So I'll stop here. We'll consider a more complicated circuit in the next class. One complication comes just by adding a resistance on the AC side. Okay, there are some other complications also. We'll look at those things in the next class.